Now we will look into the generation of sinusoidal waves by a tuned LC circuit. So sinusoidal oscillators consist of two main sections, a frequency determining device and the maintaining device. And the frequency maintaining device is a transistor amplifier with its power supply. This is your tuned LC circuit. So LC circuit. The amplifier must have sufficient gain to compensate for the attenuation of the frequency determining section and must produce the required phase shift for positive feedback. If a capacitor of capacitance C and an inductor of inductance L are connected in parallel, then such a circuit represents an oscillatory circuit. Let us consider a fully charged capacitor connected with the induction L that is shown here. When the charged capacitor is connected to inductance L, the capacitor will discharge, sending current through L and induce the magnetic field. Thus, the electrostatic energy stored in the capacitor have been converted into electromagnetic energy associated with the inductance L. You are able to see there is a charge over here and here L is there. There is no charge here and you are able to see the electromagnetic energy. When the capacitor is completely discharged, the induced magnetic field begins to collapse, sending current in the same direction. The capacitance C is now charged with the opposite polarity. You are able to see it's minus minus and afterwards plus plus. So plus plus minus minus plus plus. So once the capacitor sending the charge and electromagnetic energy is coming, so in this direction, now it's returning back, so automatically this become minus. So automatically from here the charge is coming and this become positive. So this is how the oscillation is happening. So plus minus, minus plus, plus minus. In this case, the energy associated with magnetic field is converted when the capacitor is completely discharged. The induced magnetic field collapses, sending the current in the same direction. So the capacitor C is now charged with the opposite polarity. In this case, the energy associated with the magnetic field is converted into electrostatic energy. The energy is stored in the capacitor. Once the capacitor is fully charged, it begins to discharge once again in the reverse direction, producing again a magnetic field across L in the opposite direction. Again the magnetic field will collapse and will charge the capacitor. So the circuit returns to the original circuit or original state. You are able to see the circuit is in original state now. So this charging and discharging results in oscillating current and hence electrical oscillations are set up in the LC circuit. When a LC circuit is used to store energy, it is called as tank circuit. The frequency of oscillation is given by F is equal to 1 by 2 pi into root of LC. If there is no power loss in the LC circuit, then the electrical oscillation will continue for indefinite time. But in practice, there is some more power loss during each cycle of oscillations, as some resistance is always associated with a given LC circuit. Hence, the amplitude of the oscillations decreases gradually and becomes zero when all the energy is consumed as losses. Therefore, damped oscillations are produced in a circuit. I max represent the maximum current flowing through the circuit. In order to make the oscillations undamped, the energy must be supplied to the circuit at the same rate at which it is dissipated. The energy supplied should be in phase with the oscillations set up in LC circuit. The applied energy should have the same frequency as that of the oscillations in the tank circuit. If these conditions are fulfilled, the circuit will continue undamped oscillation. You are able to see plus I max is positive current maximum and negative current maximum here. You got an undamped oscillation. So previously we have seen a damped oscillation, so it is reducing and it will become 0 here. Here it's continuing to give the same output.